Hello everyone. In this video, we will introduce a new concept, thread. We will cover the basic concept of thread, multi-core programming, implementing thread, multi-threading models, and thread libraries in 3 videos. First, let's take a look at the basic concept of thread and the difference between thread and processes. A process is a basic unit for resource allocation. A thread is a basic unit for CPU utilization. A process comprises a thread ID, program counter, register set, and stack. All this information are related to the execution. A process can have multiple threads of control. The memory space, open files, input-output devices are allocated to a process. All the threads belonging to this process share the code section, data section, open files, input-output devices of this process. All the threads belong to the same process. They are in the same memory address space. A process with multiple threads can perform more than one task at a time. This multiple thread, they can run on multiple cores simultaneously. Process creation is heavyweight, while thread creation is lightweight. The thread creation is much easier and faster than process creation. In this figure, the left side figure is a traditional single thread process. In this process, we have the code section, data section, open files, stack section, program counter, PC, and a register set. And on the right side, we have a multi-thread process. In this example, we have 3 threads in this process. These 3 threads share the code section, data section, and open files of this process. Each thread has their own stack section, register set information, and program counter information. Also, we can see this multiple thread belonging to one process. They are in the same address space. Now, why do we need multiple threads in one process? Here, I will give you an example. Assuming we have a program, this program need to read or need to play audio file. There are 3 steps. This program need to read the audio file from the secondary storage to main memory. Normally, the audio file is compressed, so the program need to decompress this audio file or the audio data. And last step is to play or output the decompressed data to a sound card to play this audio file. 3 steps. And we can implement this program like this, use this while loop, because the audio file can be very large. Now, in one iteration, we use a read function to read data block 1 and decompress function to decompress the data block 1. And then the play function to play this data block 1. 3 functions. And then in the next iteration to read the data block 2, decompress data block 2 and play the data block 2 until we reach the end of the file. Now we implement this program use a single thread process. These 3 functions, read function, decompress function, and play function, they are executed in sequential order. That means that when the read function is done, and then the decompress function can start. Decompress function complete, and then the play function can start. Because the decompress function need to use the data generated by read function, and the play function need to use the data generated by decompress function. Okay, now let's see, we have the read function, decompress function, and play function. These 3 functions, they are executed in sequential order. Now at the time 1, the read function reads the data block 1. And at time 2, the read function is done. The decompress function decompress data block 1. And then at time 3, the decompress function is done. The play function play the data block 1. And then at time 4, the read function will read the data block 2. And then at time 5, the next time period, the decompress function will decompress data block 2. And then the next time period, the play function will play data block 2. These 3 functions are executed in sequential order. This is we implement this program use a single thread process. Now, if we implement this program use a 3 thread, 1 process with 3 thread, we can increase the response time. We can decrease the response time and increase the throughput. Now the okay, now we have at time 1. Now assuming we have 3 thread. We have 3 thread, and the thread 1 execute the read function. Thread 1 execute the read function, and the thread 2 execute decompress function, and the thread 3 execute play function. So we have 3 threads. Now at time 1, the thread 1 read the data, the audio file, from the secondary storage to the memory. And then at time 2, decompress function, the thread 2 execute the decompress function on the data block 1. And now at the same time, the thread 1 can read data block 2 from the secondary storage to main memory. And at time 3, the thread 3 can play the data block 1, output this data block 1 to sound card, play this data block 1. Now at the same time, the thread 1 can read data block 3 from the secondary storage to main memory. And the thread 2 can decompress data block 2, run on the CPU to decompress data block 2. Now at time 4, the thread 1 can read the data block 4. And thread 2 can decompress data block 3. And the thread 3 can play the data block 2. Now we can see these 3 threads, they can execute simultaneously. In this case, we can increase the throughput and we can decrease the response time so that the audio file the audio can be played smoothly. This is why do we need the multi-threading. This is a benefit of multi-threading. Now the 4 benefits. First one is the responsiveness. Multi-threading may allow continued execution if part of process is blocked. A process can have multiple threads. One thread is blocked, the other thread can continue execution. This is especially important for user interface. When one thread is blocked, and the user still can get the response from other threads. Resource sharing. The thread belonging to one process by default share memory and resources of this process. This resource sharing is much easier and faster or efficient than shared memory and message passing of processes. The third benefit is economy. The thread creation is cheaper, faster, and easier than process creation. Thread switching costs lower overhead than context switch between processes. The last benefit is scalability. Multiple threads can take advantage of multi-core or the multi-processor architectures because multiple thread can run on multiple core or processors simultaneously. If we only have a single thread process, no matter how many CPU core or the processor available, this single thread process only can use one CPU core or the processor. In the multi-core and multi-threading programming, we need to know the difference between 2 concepts: concurrency and parallelism. Concurrency supports more than one task making progress. In a single processor or the single core system, the scheduler rapidly switches between processes or the thread to allow each task to make progress. Now all the processes and the thread can make progress, we have concurrency. Parallelism implies a system can perform more than one task simultaneously. The parallelism is only possible in multiple processor or the multi-core architectures. In a single processor or the single core system, we cannot have parallelism because at a time, only one process or the thread can run on this single core or single processor. So we cannot have parallelism. We only can have concurrency in a single processor or the single core system. This is an example of concurrency and parallelism. Concurrent execution on the single core system. In this example, we have 4 threads. These 4 threads, they can run on the single core based on the time sharing. And the thread 1 run on this single core for a time slice, and then the thread 2 run on this single core, and then the thread 3, thread 4. At this time period, all these 4 threads can make progress. Here we see we have the concurrency. This is a concurrent execution. The parallelism, in this example, we have 2 CPU core, core 1 and core 2. Thread 1 and thread 3 run on the core 1. Thread 2 and 4 run on core 2. At this time point, T1, thread 1 and thread 2, they run on the core 1 and core 2 in parallel. Thread 1 and thread 2, they can run simultaneously. This is a parallelism. We can have parallelism only in a multi-core or the multi-processor system. Okay. There are some challenges in the multi-threading and the multi-core programming. First one is identifying subtasks. And we have one task. If we want to utilize the multi-threading to run on the multi-core, we need to divide this task into the multiple subtasks. These subtasks are independent of one another and can run in parallel on individual cores. Sometimes it's not easy to divide a task into the multiple subtasks. Second challenge is a balance. Subtasks perform equal work of equal values. We don't want some CPU cores, they are overloaded, and this subtask run on this CPU core does a lot of work, and the other core, CPU core, is underloaded. So we want to balance this. We want to balance the task on each core. The third challenge is a date splitting. Data manipulated by separate tasks should be divided to run on separate cores. And data dependency. Data dependency means we need to examine the data dependencies between two or more tasks, between two or more subtasks. When one subtask depends on data from another subtask, we need to ensure that the execution of subtasks is synchronized to accommodate data dependency. For example, the decompressed thread need to use the data generated by read thread. So now the read thread need to start first and complete, and then the decompressed thread can start. The last challenge is test and debugging. When a program is running in parallel on multi-core system, many different execution paths are possible. Testing and debugging these concurrent programs is more difficult than testing and debugging single-thread program. In general, there are two types of parallelism: data parallelism and task parallelism. Data parallelism means to distribute subset of data across multiple cores. Each thread performs the same operation on each core. For example, we have a large array, and now we want to search a key element in this large array. Search the key element from this large array. Now the data parallelism means we can divide the data into subset. Assuming we have 4 CPU cores, we divide the data into 4 subsets. Now the first subset will run on the core 0, and this is for core 1, and core 2, and core 3. And we have 4 threads perform search operation on these 4 cores. Now the thread T0 perform the search operation on this subset. The thread 0 will search this key element from this subset. And the thread T1 will search the key element from this data subset. And the thread T2 search the key element from this subset. And the thread T3 will search the key element from this subset. Each thread runs on the different cores. These 4 threads can work simultaneously on these 4 CPU cores. And task parallelism means to distribute subtasks across multiple CPU cores. Each thread performs a subtask on each core. The different thread may operate on the same data or different data. For example, we have the array of data, and we have the 4 CPU cores. Now these 4 CPU cores, they operate on this same data on this array of data. And on the core 0, the thread 0 perform some operation on this data to calculate the sum of this data. In the core 1, the thread will perform max to find the maximum element from this data. And the core 2 performs search to search a key element from this array of data. And the core 3, for example, perform the minimum operation to get the minimum element from this set of data. This is a task parallelism. This video will conclude here, and we still have 2 more videos on threads.